Welcome, welcome. This is Chapter 4, Section 1, Exponential Functions. We're going to start getting into these. An exponential function is a transcendental function. It transcends all the basic functions that we're used to now concerning just like basic algebra. So, what is an exponential function? Well, an exponential function is probably a graph that you are familiar with, as you can see the graph here. There are a couple words that we are going to need to get into. So percent change is one word we need to go over. So that is when it's no longer a slope, so it's no longer increasing by a set amount, so by like half or 3/4 or 2 or 5. It's now things are going to change by a percent of the original amount. So think of it like a 30% discount, or over time they'll charge you 10% more, something like that. So the growth is when it is an increase over time. So the exponential growth is a percent increase over time, so it's going to get large. The decay is a decrease over time, which of course means it's going to get small. It is decaying away. There is less and less and less of it. So remember, for linear growth, let me get a pen. So remember, for linear growth, we had things that would increase pretty constantly. So if we were going this way on a number line to the positive, one point would be here, another point would be here, another point would be here, so that, as you can see, it's consistent in how it increases. Now, the exponential will not be quite like that. It will not increase consistently for a set value, for like a set amount. It will increase by a percent. So this is what we are looking at. So it can get very large very, very rapidly. It can get very, very small very, very rapidly. So we're talking about things like population, like bacteria, people, deer. Usually bacteria is something that we'll talk about. So that's linear growth versus exponential growth. Right here. So the general form of an exponential function is f of x equals a b to the x. It is b that is being put to that exponential of x. So a is just what is out front. So if we were going to use parentheses, it would be a, oh, it's a weird way to write a, sorry about that, a b to the x. And it would be this whole b to the x. That is one value. So it is not ab to the x. Don't confuse that. So a cannot be 0. What happens when a is 0 is that you just get f of x equals 0. So no matter what your x value is, you would just get the x-axis, because it would just be 0. Your y would always be 0. So b has to be positive, or else it would jump back and forth. So I will show you why. Say b were -1 and a were, let's make it -2. And let's say a is 1, because a can be 1. So we're going to have f of x equals negative 2x. So what happens when x is, we'll go with x being 0. Our f of x is equal to 1, because anything to the power of 0 is always going to equal 1. What happens when x equals 1? We're going to get negative 2. Now what happens when x equals 2? We're going to get 4. So if we were to graph something like this, you could see that when x is 0, we would get 1. When x is 1, we would get negative 2. When x is 2, we would get 4, which is way up here. So our graph would be looking something like this, and it would just keep going and keep going and keep going and keep going. And I mean, it would go off of our graph here. It would be like, you know, if you were just making doodles on a page like this. So obviously, this is why it needs to be positive, so that it doesn't jump back and forth. So b greater than 1 would indicate growth, and when b is a fraction, that indicates decay. Growth would be something f of x equals, I don't know, 2 to the 4x. Now if we had decay, f of x would equal, we'll make it 2 again, 1/4 to the x. And notice that 1/4 squared, you get 1/16. So these will get smaller and smaller and smaller and smaller and smaller. So that also means decimals on the inside, because you can have it a decimal. A fraction is a decimal. 0.25 x. So these are decay, and this one is growth. Have a look here. This is f of x to the 2x. Notice that it follows that standard growth pattern. So to evaluate exponential functions, a is known as our initial value. B is the growth factor. And this works just like any other function. You just plug in x if you want to evaluate it. Most of the time, you guys are going to be using a calculator for this. You know, because if you are asked to evaluate some function at 100, I don't expect you to sit there by hand and multiply 100 of them together. That's ridiculous. So you can use a calculator here, as long as you get the general idea. So finding an equation of an exponential function. So if we're given a point of the form 0a, we are going to take a as our initial value and put it back in for a point, and then we should be okay. And you know, you'll find another point. So if neither point is that initial point, you're going to create a system to solve for a and b, and then you're going to use whatever a's and b's you found from what you were given to again form your function. So let's try number 4. A wolf population is growing exponentially. In 2011, 129 wolves were counted. By 2013, the population had reached 236. So what 2 points can be used to derive an example equation modeling this situation? So this is an interesting one, just because of how we're going to set it up. So we will start at the year they give us. So we're going to start at the first year, and we will call that t equals 0. So in 2011, there were 129 wolves. We will take this 2011 as t equals 0, and that will give us the point 0, 129. Now when it tells us by 2013, we will have 236 wolves. If t is 0 at 2011, what is t when it is 2013? Well, from 2011 to 2012, that's 1 year. And from 2012 to 2013, that is 2 years. So here our t is 2 years later. That gives us 236 as points. So these are our points. So given the initial value, if I know this is my equation, now if this is my a, because this is the initial value point, 0, a, our x is going to be 0. Our a is 129. So that gives us our a. So this is what we're looking at if we were going to put this point into an equation. So really there's nothing we can solve for here, but that does tell us what our a is. So now if we had f of x is 2, we will have 129 b squared, because it's 2, is 236. So we will now solve this equation. So we will have 236 divided by 129 equals b squared. So let's get these factored. I know 129 is 3 and 43. 43 is prime, so that's not really going to go any lower than that. For 236, we are going to have 2. Let me see. Well, we'll definitely have 2 and 118. No, it does not look like we are going to have any. Let me see. 2, 118. And 118 would be, no. Mm-hmm. 118. Okay, 2, yeah. Another 2 and a 59. So I do not think we can go any lower than that. So we will leave it here. So the square root divided by 129 equals b. And you know what? That just looks so complicated. I'm going to go ahead and request that that be in decimal. That's totally okay. So 236 divided by 129 Then we are going to take the square root of that. So our b, and I will round this to 2 decimal places. So we are going to have 129, 1.35 to the x. So notice that everything on the inside, that 1.35, that is greater than 1, which means this will be growth. So this is just going to increase. Our wolf population is going to increase. Now, long-term model, probably not going to work out, you know, because in a couple of years, like, we're not realistically going to have a couple thousand wolves. So exponential growth models can be limited by time. Something that will affect the population is disease, the capacity to feed them. So, you know, if there's not enough elk in the area, obviously you're not just going to be having more wolves. I mean, they will be starving to death, so your population will decrease. If there's not enough room for them, so, you know, if wolf territories overlap and they start killing each other, obviously the population would decrease. So these are things that would limit that and make a long-term model like this unrealistic. So number 5, given these 2 points, we're going to find an equation for the exponential function that will pass through these 2 points. So I'm going to make those 2 points, and my first one is going to be 3, because that's my y. It's going to equal a b to the 1. My other equation is going to be 4.5 equals a b squared. So with that 1, obviously this is just going to be 3 equals ab. With this one, we can go ahead and, you know, I'm going to leave it like that. 4.5 equals a b squared. And I'm going to solve for b using my first one. So b is going to equal 3 divided by a. So now I am going to have 4.5 equals a, 3 over a squared, which would give me 4.5 equals a, and then 3 over a squared, we're going to square the top and we're going to square the bottom. So that would be 9 over a squared. And these a's will cancel out, so that I will just get 4.5 equals 9 over a. And to solve for a, I'm going to multiply both sides by a to get that a on the 4.5 side, and then I would divide by 4.5 so that I can get a alone. So this gives me 2. So our a is equal to 2. And then I can just plug it right back into here, which gives me b equals 3 divided by 2. So my equation here is f of x equals 2, 3 divided by 2, x. That's my exponential equation. So another way of doing this is we can use a graph. If we're given a graph, now the first thing we're going to do is we're going to identify 2 points on the graph, and we need to choose the y-intercept if it is possible. So looking at, I'm just going to go through it using this graph. So looking at this graph, we can see that that point is 0. Did it give us that point? Yes, it did. So it's telling us that that point is 0 square root 2. So I'm going to have 0 square root 2. And remember, this is in the form 0a. So this is why it is a good idea to choose our y-intercept, because that automatically gives us our initial value. So that's what I know so far. Now I'm going to choose another point. It looks like it goes right through 2, 3. So that means I'm going to have 3 equals root 2 b squared. Now I'm going to divide by the square root of 2. And we can just leave it for like this right now, because we're not quite done simplifying. And then I'm going to take the square root. So it is going to be the square root of 3 over the square root of 2 equals b. And here I'm just going to keep going. So I will break that up. The square root of 3 over the square root 2 equals b. So one thing to remember as the square root of anything is the same as to the half. And the nth root of anything is the same as c to the n. And these are rules of exponents from previous classes that you would have taken in high school. So it's okay if you need to look these up maybe at first, and they would be the rules or the laws of exponents is probably what you would use to go over that. So that means that I'm going to get, let me see, square root 3. This is 2 to the half to the half. And another law of exponents is if I had any number 1 over, well, actually any exponent, and it was being raised to another exponent, then you would multiply those two exponents together. So that's going to give us root 3 over 2 times 2 is 4, so that will be the 4th root. Because remember, this is 2 to the 4th now. So now I am going to have to rationalize this denominator. So I have 2 to the 4th, and notice I only have 1 2 on the inside. In order to bring out the 2, I need to have 4 of them. So I only have 1, so I need 3 more 2's. So this indicates that I need 2 to the 3rd in order to rationalize things. So this is going to give me yeah, it does say root 2. Okay. This is going to give me root 3, 4, and I am going to multiply out the 2 to the 3rd. So 2 squared is 4, with another 2 is 8. And since now I have everything here, everything will add up to 4, so I can just take a 2. So this is B. Now, I'm not going to have anything this horrible on the test. But it is necessary that you know how to do these basic algebraic manipulations. So therefore, I will have f of x is the square root of 2 times the square root of 3, the fourth root of 8 over 2x. And if you could do this one, you could do anything I throw at you. Trust me. So compound interest, and this is something that you business majors, if there are any of you guys out there listening, you will need to know this because it will probably be in a majority of your classes, along with the continuous growth model. Most business math and finance math will involve logarithms, exponentials, exponents. So it's very important that you know how to work with these things. So when a savings account or investments account, they continually reinvest the interest, then that is compounded interest. So what that means is that I take the interest you make. So if it's 10%, and you put $100 in, at the end of the year, you get you get $10 back. So I give you that $10 in your interest, and then I continue to let you earn interest on that interest. Now, of course, this may sound obvious, and some of you are like, well, duh, like what else does the bank do? Well, they do have simple interest, which means that if you put in $100 initially and you are earning 10% annual simple interest on that, you will get $10 at the end of the year. And your bank account could reach $400 billion. Like, that's how, I know that sounds ridiculous, right? But we're just going to pretend that you live forever here. And, you know, one day your bank account is like $400 billion. Well, with simple interest, you are still only making $10 a year in interest. So there are actually different types of interest. And as business and finance people, you will go over these later. But the point here is to see the application of some exponentials, and we see that in interest formulas. So the APR is also called the nominal rate. So that's the yearly interest rate earned on the investment, the annual percentage rate. When it's compounded multiple times a year, so what that means is instead of giving you interest at the end of the year, I can give you interest, you know, at the end of the week, at the end of the day, at the end of the month, whenever I choose my compounding to be. And what that means is that I take that interest, put it into your bank account, and then for the next period of interest, you are earning money on that interest. Whole lot of the word interest, it will be thrown around a lot here. So the effective rate will be greater than the nominal rate. What that means is that what effectively is happening, so what is going on in your life, will be slightly larger than the nominal rate, the APR that they give you. And this is the formula for compound interest. Do it in orange. That is the compound interest formula. T is time. P is principal. Your principal is the initial amount you put into the account. So if I open a bank account with $25,000, or if I open, I'm sorry, not a bank account, let's say a savings account. If I open a savings account with $25,000, that's my P, my principal. The annual percentage rate is that APR, what they give you, the nominal rate. Compounding periods per year, that would be quarterly is, 4 times a month. A quarter, there are 4 quarters in a dollar. So there's 4 quarters in any one year, any unit of time. What's another popular one? Monthly. So that would be 12 times per year. Biannually would be twice a year. So AT, account value at time t. You will also hear that called future value. There's another form of this equation that some of you may have seen, where it would be future value equals present value 1 plus r over n nt. This may be another, this was common way to show it when I was in school. So we will have, and let's use try it number 8. So we're going to have an initial investment, remember that's our P, of $100,000. And a lot of these investment questions will involve very large sums of money, incredibly large sums of money. So that's normal. So the 12% interest is our APR, and that has to be in decimal form. And that is compounded weekly. Later, when you get into things, you'll find out that, some people, maybe a year isn't quite a year, but we're not going to worry about that right now. That is why it says use 52 weeks in a year, because sometimes a year is not quite a year. So it is compounded weekly. So the number of times it is compounded is 52 times in 1 year. And they want to know what it will be worth at the end of 30 years. So A of 30 is going to equal 100,000 times 1 plus 0.12 divided by 52. It's going to equal 52 times 30. That is quite a lot. So let's see what we have got going on here. 0.12. I recommend doing inside the parentheses first, divided by 52, plus 1. And do not round. Do not round anything. Just keep doing it all in your calculator and do not round anything until the end. So this is first. And then I'm going to say that will be to the power of there's power. To the power of 52 times 30 times 100,000. So now I'm going to round. So you will have $3,644,675.88. Now I prefer you round to the cents like it's dollars. I do prefer that, actually, yeah. So keep it at 2 decimal places. Now, continuous growth. Now, this happens when it's like every second of every day, we're constantly putting in interest and we're earning interest on that interest and more interest and interest and interest. And there's so much interest that the interest has interest. So this is what I mean by continuous growth. It's just a ridiculous amount of interest. Yeah. So this is when we use base E. So E is it is not a variable. Please. I cannot even tell you how many times every single year I have this same discussion and I get people who email me or come up to my desk wanting to know what the value of E is because it wasn't given. E is a button on your calculator. E is an actual number. Google it if you don't know what it is. I really encourage you to Google it yourself so that you see it's a number. E is not a variable. It is not a variable. It has not been a variable. It will never be a variable. Please do not email me asking me what E is because I left it out of every problem. E is not a variable. It is not a variable. Okay, moving on. So investigating continuous growth now. The function is a to the t equals a e r to the t. E is to the power of r to the t. So a is your initial value, r is your continuous growth rate, and t is the elapsed time. So notice that if r to the t is negative, it will go down. And if r to the t is positive, it will go up. And this is because, so if you have some number and it is to a negative exponent, then what that means is that that number and exponent are actually the bottom portion of a fraction. That is what that means. And also notice, it also means that if you have a number with a negative exponent on the bottom, you can just bring it up. So if it is a negative exponent, it belongs on the opposite side of your fraction bar. That is why it is growth versus decay. So notice that r is what would be negative, not t, because t is not negative, because that means we are in a time machine and we're, going backwards, which we're not going to touch on that, whether or not people think that's real. But as of right now, you can't really go onto Amazon and buy a time machine. So we're not going to count when time is negative because it's just not possible for us. Now, notice when it is business related, it is called the PERT equation, like that old shampoo for dandruff, PERT Plus. I don't even know if it's around anymore. Where now your initial value is equivalent to your initial investment, which makes sense because it's your starting investment, your starting value. So if someone was to invest $100,000 at a 12% interest rate per year, compounded continuously, this is what we're looking for to use E, continuously, compounded continuously. What will be the value of the investment in 30 years? So we're looking for in 30 years. We know our initial investment P is $100,000. Our interest rate is 12%, and it is compounded per year, once a year, continuously. So that's 0.12, 30, because our T is 30. We want it after 30 years. And remember, your rate absolutely has to be in decimal. So you can't just put 12 here because that wouldn't work. So remember, E is a button on your calculator. You're going to use that, and you're not going to round at all until the very, very final answer. So it will be worth $3,659,823.44. So let's see. Yes, here's our previous, when it was just compounded, I believe, every week. And here's what we have when it is compounding continuously. Notice that it is actually larger. and it is larger by about $15,000 over the course of 30 years. So it's about $500 a year extra when it's compounded continuously. So a little under, you know what, $50 a month or something. Okay. Don't know why that one is on here. All right, so this is 4.1, exponential functions. We will go through the graphs later. Thank you for watching, and I look forward to seeing you in the next one.